So now I actually want to continue doing the Hidden Fortress puzzle, okay, the featured puzzle of this week. And I was doing it halfway just now before I needed to go out. So actually on the way out, okay, so for those who don't know, this puzzle is basically like this. You have a series of numbers, and each number of the grid, okay, I mean it might also be letters, but it just actually means a number. Okay, each number means like how many column and how many how many O's are there in the actual column and row of each element. Okay, so like over here, number two means that there's like one O here and one O here in the same row or column. So there's total of two. So like three over here is because there's two on this column and two and one two on this row. So total you have three, two plus one, like that. So initially I did write some code to like check constraints and everything, but actually I realized something. Okay, I realized something. Okay, I realized about this. I call it the layer cake principle. So like every time you add a O over here, you will just add one to anything in the row and anything in the column. So essentially, what this means is that whenever you still have an O, like whenever you still want to figure out whether a piece is an O, what you can do is you can just take the sum of these numbers, whichever is the highest. Typically, that square will be an O. Okay, so I tried using this method, and I mean you can see, I just iteratively remove the square. Okay, but I face an issue. Okay, the issue that I face is that like I solved the 3 by 3, I solved the 5 by 5, but when it came to the 11 by 11, there's some discrepancy in the output. Like I predicted this, but the expected is like that. So it means that if I were to do like the layer cake principle, okay, the layer cake principle, let me just explain again. It's like this: you just take the row, the sum of all these numbers for the row, sum of all these numbers for the column. And then ideally, if there's still an O piece at that position, because of the nature of the fact that once you put an O inside here, you add one to every single column and you add one to every single row count here. So by right, the square that has the highest sum of the row and column, okay, it should still it should be the most likely to contain an O, isn't it? Yeah, so I think that was my logic back then. Then I was thinking about it like, could it be that if let's say the sum of the row and column is the highest, could it be not because that there's an O at that square, but because all these numbers over here, all these numbers are also influenced by the other columns. And similarly, all these other numbers are also influenced by their rows. Could it be that there's another piece here that's driving up the numbers here? And just so happen that this is like the highest row and column. So I was thinking about it like whether this layer cake approach, how do I make it work? So I was thinking and I came up with a solution actually. I'm thinking that maybe I shouldn't. I mean, I haven't tested the solution, but this is my thought process. I'm thinking maybe we shouldn't just take the sum of all of these numbers here in the row and the sum of all these numbers in the column. We should just take the minimum number for the row and the minimum number for the column. This should tell us like, because like let's say if this is two, it means there's like very few squares can have this. Okay, so if it's a two, it's probably not going to be on this square, but it's going to be one of these squares. And the most likely case is if the number is the highest, of course. So we take the minimum of this row sum and we take the minimum of this column sum and we add it up. And then wherever the intersection is, like over here, the minimum here is 2 and the minimum here is 2. So 2 plus 2, this position has a value of 4. And this position has a value of 0 because minimum 0 and minimum 2. So this is value of 2. So using that, you can actually sort of figure out which one is like the most likely. So this one is like 2. This one, minimum of 1 on the row and minimum 2 on the column. So, this is likely going to be a piece as well. So, yeah, I mean, using stuff like that, it could be possible to tell. I mean, I wouldn't say that it definitely, you can definitely can tell, but I think that there's some merit to that. So instead of taking the sum, okay, we take the minimum. So I'm not sure whether I can just do minimum like that. So it will be column sum plus row sum, okay, minus away. Actually, I don't need to minus anything now. Yeah, in fact, I don't even need to see whether it. Yeah, I think I can make it very, very, very simple. It's just similar. It's just the column sum and the row sum, the minimum, and then I just take the argmax and then I subtract away. So we just check whether this works for the 3 by 3. Oh, something's wrong. Oh, okay, don't know why it took so long to check. So this work if I take the minimum, this work if I take the minimum. This 5 by 5, oh, unfortunately it didn't work. Okay, so why didn't it work? Let's see the answer for the 5 by 5. Oh. Okay, maybe what I should do is I should just print out. Okay, at the end of it, I should just print out the cell count so I can see like what's wrong. So in the end, I got like minus. Could it be that I did it wrongly for this? Column sum, row sum. I'm not sure. Did it predict the right number of pieces? I think it may not predict the right number of pieces. Like over here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So apparently it might give values that have already been placed. So it means that maybe the original constraint that I put here was necessary. 1 minus fortress, okay, times dot reshape minus 1. So this will tell us where, if let's say there's a piece there, then this will give it a value 0, and then the argmax it should ignore these values. So let's try again. Okay, I guess I printed this out, so let's remove this printing lines. 3 by 3 works. 5 by 5. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay, let's see the cell count now. Okay, still did I mean this heuristic didn't exactly work. Just taking the minimum of both the row and column was not sufficient to guarantee that I removed the right thing. So like over here, we take a look here. 5, this is minimum of 5, this is minimum of 2. So actually, this 5 and this 2, maybe I should not only take the minimum, I should also take the sum. I'm not sure whether the sum helped, because like the 5 by 5, if I took the sum, actually that kind of worked. So this was the minimum. This was the minimum. I thought I solved this problem, but apparently just taking the minimum is not sufficient. I mean, this minimum here is correct. The 3 by 3 worked, but the 5 by 5 it didn't work. Yeah, so maybe taking this minimum itself was not sufficient to guarantee that. So maybe I do a min call sum, min row sum. Okay, then over here is call sum and row sum. I'm not sure. I mean, I think this might account for it because it gives both the minimum and as well as the column sum. Let's hope it works. Okay. Oh no, it still didn't work. There's still a -1 here. I mean, if I try the 11 by 11, yeah, it is not the most accurate solution. Oh, I know why, because I forgot to minus away the actual cell count itself. So I duplicated my counting. So let's see, 0, 0, 0. This works. Okay, this works. 5 by 5. Oh, it works. Okay, 11 by 11. Oh no, it didn't work. See, 11 by 11, there's still like cases whereby if I just do this greedy approach, it doesn't lead to the right solution. How about 16 by 16? Yeah, it still doesn't fully work. Okay, so I don't think I've solved this problem yet, which is good. I mean, I can spend some time thinking about it, but at least for until 5 by 5, I have solved it. Okay, it works, just doing this min row sum and min call sum. Let me think about it again. I mean, if I want to figure out that there's a position here, okay, I need to, like, this is a 5. Okay, there's going to be 1, 2, 3, 4, 5. So if let's say the column sum is like the minimum over here, should I take the minimum of the, so I take the minimum here, and because in the layer cake principle, the chance of, let's say, something being very high, like over here, the minimum for all this and all this could be very high, but this position may not have anything at all. Yeah, I mean, it just could be the fact that, like, I have a lot of O's here and I have a lot of O's here, but this position doesn't have. Yeah, so there's this risk. So this greedy approach has its pitfalls in this sense. Yeah, it needs to have other metrics to align it, I believe. So if let's say all this here are very high, all this here very high, this is the highest. It might be because this is like having the most. Mm, I'm not sure. I mean, there must be a way. I mean, the other way to solve this problem is to use linear algebra. Not too sure whether like is there a way to there's a way to do it. Yeah, I mean, I could use linear algebra to solve this problem. Like, you have this a, which is like this kind of equation, 1, 2, 3, 5, and then we have this constraints here, and then we'll try to solve this, and then this will give you whether or not it's -1 or 1. So I guess if we use linear algebra, it might actually just work. I mean, I don't mind trying that. I mean, because it, essentially this is like a linear algebra sum. Like, if this is 2, it means that a, b, c plus this plus this one plus this one, like 1, 2, 3, 4, 5 give you 2. Then you have to solve like a series of linear algebra equations. Uh, it's going to be like size squared number of equations, but it's still possible to solve using this. Yeah, I mean, this is one way to do it with linear algebra, I guess. I'm just quite sad that this didn't quite work out. I thought this might work out, but apparently just using the min may not work. I don't know. We're using the max work, but max it will just be itself. How about max excluding itself? Okay, how do I do this? Okay, if I want to do the max of that row itself excluding itself, uh, no, I don't think there's an easy way to do it. I don't think there's an easy way to do this. I mean, if I were to do the minimum method, it's still okay. Okay, but let's say if I want to find out what is the maximum of this row and column without referring to this at all. Okay, because maybe this might like be the case where here and here all have circles, but this position doesn't have. So I want to take away this position. I just take the max of whatever's remaining and max of whatever's remaining. Maybe that could solve the problem. Okay, I'm not too sure, but if not, I have to rely on like linear algebra, which I try not to go here. Yeah, I try not to go here. I mean, it's definitely possible to do this. Yeah, I mean, it's actually pretty easy to try to solve this using linear algebra. But I try not to, okay, because I feel like this problem you can solve it without linear algebra. I hope. So let's see, okay, whether or not I can do it. Okay, let me just expand my code a bit more. Okay, so the logic is a leave one out max, which doesn't take into account the position of the piece itself that I'm doing the sum. So like if I'm doing the minimum column sum, I take the axis. Okay, I want to remove itself. So yeah, I guess what I can do is for I in range. Yeah. Okay, so min call sum will be like that. Okay, and then we just append. Okay, this mp.min. No, but actually, if I do this, I actually need to do a column sum for, instead of just having one number, because I do a leave one out, my column sum for this will be like one, and then my column sum for this will be like two. It will be a little different. It it will be a different value for each column. So like let's say if I want to take the column sum of this and this, it really depends on which index I'm taking. So if I'm taking from here, then it will be here, and if not, it will be here. So what I can do is I can do like that for j in range cell count. Okay, min call sum dot append. Okay, mp dot min. Okay, cell counts I comma j. Okay, I'm thinking how to do this. Okay, so if j is my cell in question, so it'll be I to j plus. I wonder if I can concatenate the array straight away like that. Mm, okay, so I want to do a leave one out. Okay, let's think how I can do this. Min call sum dot append mp dot min cell count I until j. Okay, and then this one will be j plus 1 onwards, like that, min. And actually we can do the min row sum as well. Let me just copy and paste this whole thing. mp dot main cell count, and then for row sum it will be doing the exact same thing until I is j, and then I plus 1 onwards, and this is j. Yeah, let's do this. And then what we do is min call sum equals to min mp dot array min call sum shape equals to size. Min row sum equals to, I wonder if I can do this. Let's see the mp dot array. Can I do an mp dot array with software and game development, is it? Yeah, sure. I can add that in. Yeah, maybe I just add it now. Software and game. software and game development. What's the difference actually? Software and game development and the science and technology. Okay, I guess it's software, yeah, but okay. So I think coffee cafe. I don't think depth first search can solve this problem. Why? Because there's just too much depth to search. I mean, if you look at it, it's like 31 times 31, right? And you assume that, let's say you fill up the grid, about half the grid. So 31 by 31 is like 900, around 900. And you take half the grid, that's 450. So if you fill up 450, I think you need to search through a depth of 450, and the amount of possibilities is like exponential. Like it's like almost 450 factorial kind of possibilities. So I don't think that first search will work. You need to do some form of greedy search. If not, you might need to use like linear algebra. Okay, so I'm trying to do an ingenious way of like trying to find out which is the most optimal place to put an O. And I'm trying to do like a leave one out minimum. So like over here, I ignore this square. So this square will take like the minimum here, so it's 5, and the minimum here is like 2. So yeah, so that it doesn't like conflict with this. I'm not too sure whether this will still work, because like in the event that like here and here, like all these rows and columns all have O's, this number here will be very high, but the rest will be very low. So still not sure whether this will work. I mean, you need to remove like one by one, all these like crosses over here. It's a tricky problem to solve actually. Yeah, I'm thinking of a way to greedily, like let's say if I look at this grid here, can I immediately tell like which position has an O straight away just by looking at this grid? And the answer is actually yes. Like you look at all these points with 7, right? Usually they will be the ones with an O. Usually. But I mean there are cases where it might not be. Here's a bit hard to look because here is like, yeah, like over here this is a C, okay? C means a lot. But then this position doesn't have a circle. Yeah, but then if you like do a summation of the rest, you can like sort of probably see that the rest are not there. I have to think about it. Yeah, but let me just try this leave one out thing first. So mp.array, and then I guess I cannot do the shape here, so I have to do the reshape later. Dot reshape size. This problem is proving to be harder than I thought it was. than I thought it would be. Yeah, I mean, I thought this would be good enough already, but apparently not. Let's try this. Only integer scalars can be converted. Uh, oh, this should be size, not cell count. Range size. Zero size array. Okay. Okay, how do I concatenate mp.array? Yeah, I guess I can use two one-dimensional arrays. Okay. I still don't think this would work actually, but I don't know how else to make it work. So I'm just gonna run with this first. Np.min this one like that. Yeah. Okay, let's see that whether the brackets make sense. Why are there so many brackets? Okay, there's some. Okay, so I don't need this min anymore. Okay, looks good, I guess. Is there an error? This should work, right? Like that. Concatenate, min, append. Okay, not sure if this will work. I think it still wouldn't work. So this one will be until I, j, then I plus 1 onwards, j. I don't know. Yeah, I mean, that first stretch with max positions also wouldn't work because the max value positions may not be the 150. It may not. See over here, like this one looks correct. The 5 by 5. Oh, this works for the 5 by 5. Okay, I mean, I knew it worked. Oh no, but it's actually an improvement. Using the leaf one out, you see over here, the minus one, 1. It's not that bad. I mean, it's just minor tweaks. We can actually solve this already. Because you see, over here, there's some positions that are like you can just swap this element with this element. You can like potentially solve this question already. Uh, I mean, it's generally like almost there. This one. This is definitely not almost there. This one still have quite a bit of work. 21 by 21. It's also almost there. So actually, the layer cake approach can work for most cases. Let's try the 31 by 31. So I think there must be something that I'm. Oh yes, timed out. Oh wow. Yeah, it's actually almost there. So I think there's some merit to this method of solving. Okay, I mean, if let's say I don't use the mean row sum and mean column sum, let's just take this out, take this whole thing out. I don't put this in here. Actually, it leads to about the same performance, I would say. It's almost the same performance. 5 by 5 would solve. Okay, 11 by 11, almost soft. Okay, there are some changes that needs to be done because like all these are ones and all these are minus ones. Yeah. So maybe what I need to do is, I mean, initially I did. Okay, let's take away this leaf one. Let's take away the minimum. I don't think the minimum really helps. Okay, if I were to take column sum and row sum, and then I multiply by whether or not it has been done before, like whether it has been taken out before. Uh, no, I tried to use like the minimum of the row and the sum as an additional heuristic, but it did not exactly take out the right thing. So I want to greedily take out um, the right cell, so I don't have to do depth first search with backtracking. I think that is too slow for this problem. I need to really, based on the board state, be able to dissect where exactly is the where exactly is a particular like circle located. Oh, yeah, okay, yeah. I mean, the idea of my layer cake is like this. See, when you add in an O, okay, your rows and columns will all be added by 1. So like over here is like you add 3 times, so it's 3, and your column here be 1 1. So my naive thinking is that if I take the row sum and the column sum like that, okay, whichever is the highest, okay, out of any, you take the row and the column sum, okay, whichever is the highest, okay, it probably means that that place there, okay, has an O. So that's my naive thinking. Yeah, so I'm just taking the for each cell, you take all its row numbers, and then you take all the column numbers, and that then I just sum up all of them, and then my naive thinking is that if your sum of your row and your column numbers is high, it is very likely that that position has an O. So that kind of thinking has served me well until 5 by 5, because 5 by 5 it works. Okay, but 11 by 11 you can see that actually there's some stuff that, like you see -1 over here. So maybe now what I will do is I will implement a constraint. I'm not sure. I think it is solvable by linear algebra, and I did have like over here. You just need to reference like over here, like you give a sum like a 1 0 0 0 0 0 1. So you basically fill in this thing, okay, with your variables, and your variables are like your row and your column. Uh, all these are your variables, and then like this number over here, which is like the second number, um, which is this one. Yeah, this will be the input to your linear algebra for your second array, and then you try to solve. And when you solve it, your 0 and 1 will then be the output. So if my what do you mean nobody solved it? No. People have solved this problem already. I have two of my friends like Murat. One of them has already solved this problem, so I think it is solvable. But I'm not sure whether people use linear algebra to solve it. Mm, yeah, all score is 0. I'm not too sure. Maybe I haven't really seen, because maybe the results are not out yet. You see the results here? Yeah. Okay, let me try to think of how to. Maybe if I add a constraint, you see, like over here, there's a -1. Maybe if I add a constraint that you cannot take away positions that have a row sum or column sum of a minimum of 0. Okay, let's say minimum of 0, and then you minus it will lead to a -1, then you cannot. Okay, so looks like I need to do the minimum thing again. Okay, okay, so basically what I will do is I will add in, okay, min call sum, okay, and then this one will be mp dot min, this one will be equals to 0. Yeah, because if any of them equals to 0, then we don't want to, okay, we don't want to put in this. So maybe like minus 5,000 times min call sum 0 minus 5,000 times min row sum. Yeah, so basically these are like constraints to make sure that these are some constraints to just make sure that I don't subtract zeros from the row and the column. Let's try for 3 by 3, see whether this still works. This works for 3 by 3. 5 by 5 is it still works. 11 by 11. Oh, okay, so it's weird. Okay, because if let's say your min column and min row sum is 0, and you subtract, actually you can still subtract it. Why? Yeah, that's why. That's a curious thing. So it could be that even though I made it minus 5,000, but based on the way that we have, based on the way that we remove it, okay, based on the way that we remove it, it could be in a case whereby even if I subtract 5,000, that is the best possible move to take, because there's no other way to violate. I mean, all other moves will violate this assumption. So let me just see the 31 by 31. Actually, it became worse off if I were to put this thing here, because like then it will go to another solution. Then you see here's -2. If I didn't put in this thing here, okay, maybe I just do a like minus like that. If I make this like a very small penalty term, it is like neural networks, like it is like a regularization term, I guess. Okay, so it's -1 times this. Yeah. See, if I make this term very small, it doesn't go to minus 2. Actually, this to the final solution is very, very, very close. Yeah, it's really very close. You just need to swap a few more. No, it's not a standard algorithm. The layer cake is my analogy of, like, your there's this cake called 9-layer cake that has different layers one by one. So I'm just using the analogy. If I stack up one layer, it's supposed to elevate the ground there higher than its neighbors. So based on that, oh, no, 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 I'm not using that for search. My layer cake is really just analogy to like how the 9-layer cake is made. So you have one layer, then you stack another layer, then you stack another layer. So if let's say you place a piece, you are like essentially placing a cross on the landscape. So if I place a piece and I place a cross on the landscape, theoretically, if I sum up the row and the column, it's supposed to be like the highest out of everything. And then, yeah, you know what? Actually, let's just use the linear algebra method. I'm not too sure like how exactly I'm going to, yeah, but I'm just worried about this method because if I use this, there might be more than one solution, and it might not be. Can I limit my range of the solution? No, I think it should work because in order to solve it, everything should work. Yeah, so maybe I should use linear algebra. I mean, I tried using a greedy approach. I do like the layer cake approach. I take up the sum of the row and the column, and then my naive thinking is that if all this row and column numbers sum up the highest out of the entire grid, okay, then it's the most likely place to put an O. I mean, that kind of makes sense actually, but there can be cases whereby, let me just draw it out here. There can be cases whereby, I can have like two O's here, and then by the layer cake algorithm, okay, so this one will be 1, this one will be 2. Okay, let me just calculate this again. So this one will be 2, this one will be 1, this one will be, no, this one will be 2 also. This one will be 2, 2, 2, 2. Or is it 2 for everything? Okay, let's see whether this works. Okay, so this is actually 2, 2. Oh, this is actually 4, not 2. It worked actually. So you see, by the layer cake algorithm, I'm supposed to assign my highest value here, right? Because 2, 2, 4, 2, 2. I'm supposed to make this an O. Somehow it didn't make it an O. That's weird. Okay, let me just print out how this does it. Because I was worried about this case. The night. Yeah, yeah. So I'm trying to find out the best cells to put the O by using this layer cake heuristic. Yeah. So definitely the heuristic is very, very important. I love heuristics. Yeah, heuristics help to. So this is my words. Okay, if you have a heuristic, okay, you can essentially do what your depth first search can do without the depth first search. So a heuristic is like a depth first search condensed into some. So if you know the structure of a problem, the heuristic can help you, like, without evaluating the entire search tree, you can already find out what exactly the outcome would be because of your heuristic. So Alpha Zero, this kind of like game playing programs with Monte Carlo tree search. If you use like their policy network or their value network, that is like a heuristic. Okay, it's just that it's using a neural network to encode that heuristic to tell you how good that move is, so that even without that search itself, okay, the heuristic, if it's robust enough, if you train it long enough, okay, that heuristic itself can help you win the game already. Like tic-tac-toe can be played with heuristics as well. You don't need to use that for search. Yeah, this is an argument against that for search. Yeah, sorry, sorry, omniscient, but I don't quite get how you got 30 to the power 5 for this problem. Yeah, I don't think this is an argument against that for search, rather an argument. I'm looking at Coffee's your comment. I don't think this is an argument against depth of search, rather an argument against starting with highest value. Oh, okay. Yeah, I mean, I'm just using a naive heuristic here with the highest value. Actually, I'm very surprised why this works because you see, by highest value of the layer cake argument, I'm supposed to give the first O to be here. So let me see why. Okay, why it didn't. Okay, so over here, 2, 2, 2, 2, 2, 4, and then what it did was that it took. Oh, I know why already. Because the top here also sum up to, yeah. So if let's say we were to toggle the grid again, we make the 4 over here, then I think this would fail. Okay, so we do it like that. Yeah, so this will be the case that I wanted to test out, and you see it failed. Yeah, so this is the reason why my algorithm fails. Okay, because if we do it greedily like this, in this layer cake approach, I need to solve this problem. Okay, this is the problem that causing the algorithm to fail. Okay, if let's say there's this 4 over here, okay, but there's nothing here. I mean, yeah, there's a 4 over here, but there's actually nothing here, and everything is actually down here. I need to find a way to like, so if just purely using the layer cake approach, I would put my piece at the 4. Okay, but putting my piece at the 4 over here, okay, would not lead to the right solution. Okay, so what does this mean? I need to put my piece at one of the twos. Okay, but what two should I put at? I should put at the two that has this 4 here. Yeah. So I think what should be done is like, I should subtract away everything from this cell itself. So like, I should just count its neighbors, like 4 plus 2 plus 2 plus 2. I shouldn't count the cell directly. Okay, I should count its neighbors. So what I can do is, okay, I don't need this min sum anymore. I think I realized the problem with this heuristic. Okay, you take the call sum, you take the cell count times 2. So we just want the layer cake without that particular point itself, so to avoid this thing. So it's actually like in order to take the first point, I just count this 2 plus 2 plus 2 plus 2. So then it knows that, okay, the contour around it is quite low, so it definitely won't be this. So I should count the number not as the number itself, but as the result of the people around it. Yeah, so I think this is something like leadership. Okay, to evaluate a leader, you don't look at his attributes, you look at the attributes of his people. Okay, I mean, I'm just giving an analogy here, so maybe this might work. Okay, let's, if I can solve this test case, I think I can solve the problem. Okay, unmatched, don't know what. Okay, um okay, I think I need to put another bracket here. Oh, I solved it. Okay, so this worked. Okay, so it's okay. So let's pray hard that that this layer cake works. Okay, I printed out something. Oh, I'm so excited, whether this works. No, it still doesn't work. It still doesn't work at the 11. Oh, what is wrong? What is wrong? Oh man, I thought I got it already. Okay, let's see. Okay, I mean, I found out a test case that it didn't work. Okay, but let's see why isn't it working. Okay, let's print out the cell count. Okay, maybe we just print out the cell count for the last one. Just print out this. I mean, at least I ironed out one kink there. Okay, so I print out the cell count for this. Add this position into the final solution. Okay, so apparently just taking the people of it is following wasn't sufficient to solve this problem. I'm still faced with it. I mean, let's see the 31 by 31. How bad is it? It's not very bad actually. It's like almost there. You see, everything is -1. I just need to swap a few ones. You know, I'm even contemplating if you invert. Sorry, if you invert your output and get back the starting value, the test case is broken. Oh, you mean this one? Invert this one? Yeah, I mean if you can use this test case you generate and get back this thing here, then you have solved the problem. Yeah, that's exactly what we are trying to solve. I wonder if neural network can do this. Like you pattern match this one to this. Maybe they could solve it. But anyway, I'm just thinking. See, it's almost solved already. I almost solved. The amount of one and -1 is like so little. It's just it's just about tweaking some positions with the one and -1. I'm just thinking whether I could do a back processing. So like after we do the greedy approach, okay, then we swap places whereby the greedy approach fails. Like okay, let's analyze this one. So you see -1 and 1. Is there a pattern we can find here? So if you look over here, like this row and this column, there's basically there's one less here and one more here, and then there's one less here and one more here. And if you look at the answer is okay. This was 11 by 11. Let's see the answer for 11 by 11. How far off are we? So if you compare this to this one here, oh, so we are missing. We this one and this one is at this position, and then this one is at this position. And essentially that's one of the swaps we need to do. This one and this one need to swap. Okay, and then there's another swap that needs to be done. This one here needs to come here. Yeah, so if we look at this grid here, if this whole thing is 1 and this whole thing is -1, it means that this one need to swap with this one if the entire thing is 1 and -1. So after we swap this one, okay, all this will be zeros. And then when we see something like this, -1 here and 1 here like that, the -1 should go to the 1 position, and the -1 here should go to the 1 position like that. Yeah, I wonder if we could do layer cake. How can we find how many O's are there given the grid values? Oh, you can just simply take the every single element, the row and the columns. Let me teach you how to do it. You take all these numbers, you add them up. Okay, then you know that each O here will be replicated by 1, 2, 3, 4, 5. So in a grid of 3 is 3 times 2 minus 1 times. So you take the entire sum of this thing and then you divide it by size times 2 minus 1. So actually, initially I actually did it, okay, to get the number of pieces. But I mean, let me just show you how to do it. Num pieces equals to sum your cell count, okay, and then you divide it by size times 2 minus 1. Yeah, that's how you get your num pieces, your number of O's. Yeah, I hope that answers the question. Yeah, that was the easy problem actually. Yeah, the problem is how to put no, not every number repeats 2 times. Every time you put the O in that position, like you put the O in this position here, it affects the values of 1, 2, 3, 4, 5 pieces. So every O will add 5 to the sum. Yeah, I mean depends on the grid size. In a larger grid size, it will add more to the sum because it affects more pieces. Yeah, so you just divide by like size times 2 minus 1. That's the effect of adding one piece. Okay, so I'm thinking actually, it doesn't look too far away. See, like over here, the -1 and 1, right? I'm thinking whether or not I could just like take this 1 and -1 and then like do some form of rescue. But over here, like need to swap quite a few pieces. It's not that straightforward. Yeah, but it does look like we can rescue it. How do I invert the grid though? Yeah, so like over here I have some issue because like this one and this one needs to swap in the final solution. My greedy method didn't really work out. I think if the cells are more than half populated, maybe you invert the grid. Mm, but if I invert the grid and I take the minimum, wouldn't it be the same as I take the maximum of, I don't know. I mean, a minimization of the negative problem is the same as a maximization of the original problem. Yeah. I mean, this layer cake approach is that's my own name of saying sum up all the row and column. Yeah, but it's almost there. It's almost there. I almost irritated that it didn't work. Yeah, it's almost there already. Is it like this minus one, right? It's minus one. I just need to swap this column here and this column here, and then this would work already. And then of course, like this one and this one. Yeah, we need to like swap this thing with this one. Yeah, but actually, this solving this problem is actually difficult. Yeah, because this one involves you to find like row and columns that sum to like a cycle, and then you need to compare with the original O. So actually, solving this problem is still difficult. I don't know. Maybe there's a heuristic that can solve it, but this layer cake approach can only solve certain kind of problems, like 5 by 5 like that. It's solved. But when it comes to here, maybe I'm missing out something. Maybe I'm missing out something. Let's try again. Like maybe a 3 by 3 custom. Let's try to make this code break. Let's try to break it. Okay, let's try to find cases whereby it doesn't work. So I'm just adding one more O here. See whether it works. Okay, so this worked. Okay, how about I remove this here like that? Mm. Okay, I try this again. I try this test case 5, and then given the total number of O's, how can you find how many O's are there in a particular row, right? That can be done as well. Okay, that can be done. So in order to find out how many O's are there in this row, okay, what you can do is like you can just take the numbers here, like 2 1 2. Let's see. Hmm. I think I kind of knew how to do it just now. Maybe you have to take like the minimum of. Oh yeah, you can't. But definitely the number of cells in this row is definitely going to be less than one. So you know that since it's zero, there's 0 cells in this row. Maybe there's a way to do this. Like if you look over here, the minimum here is 2. Okay, it means that this row has like the minimum. Then here minimum is 3. This row has 2. It's not straightforward. That's a good question. If you can find out how many O's are there in each row and how many O's are there in each column, you essentially solve this problem. Yeah, you're right. I mean, there's this game that actually gives you the number of things in each row and column, and you solve it. Yeah. Okay. Let's say we start with the largest row. Okay. Look at this case. We start with the largest row here, 3 2 2. Where are you gonna put your O's? Gonna put it here and gonna put it here, right? Like over here, we start at the largest row. You're gonna put it here. Yeah. The problem if we use like Sudoku methods is that Sudoku takes quite long to solve already if you use Sudoku methods. Yeah. What's the OM, by the way? Can I ask? Sudoku OM. Yeah. Sudoku is just a, if you think about it, it's just a 9 by 9 grid. Okay, let me try to put like one O here and one O here. Okay, so it means that I need to add these numbers here by one. So that will be 4, 6, 5, 6, and then here will be 3, 5, 3, 4. And then this thing here will add by one also. Will add by two actually. This row will add by two. So I put 8, 6, 6, 4, 7. Okay. Solve. Oh, okay. Yeah. Is there no good heuristic to solve this? I'm actually quite curious to see like what other people have done, but I don't want to look at it right now. Yeah, I want to solve it on my own first. Uh, shall we use linear algebra? I mean, I'm out of ideas for the heuristic. Yeah, I'm out of ideas. Yeah. Shall we just solve it with linear algebra? Yeah. All right, so let's solve it with linear algebra. Okay, so how do I do this? Let's copy the linear algebra here, like that. Yeah, this is an interesting problem. I really like this problem, and I'm a little frustrated myself for not being able to solve it with a heuristic. Yeah, I thought the find your neighbors total sum heuristic would solve this problem, but I was wrong. I'm surprised. Yeah, the find your neighbors sum thing seemed quite intuitive to me. I almost thought I solved it. Yeah, I almost thought I solved it, but I didn't, and that was a little sad. Oh well, okay. Let's try to solve it with linear algebra. So, assuming let's say I want to code this over here, so my array two here would just be like it would be cell count. Okay, and my MP array here would be like, yeah, 0, 1, 1, 1, 1. Okay, so it will be a few numbers. Okay, it will be 1, 4. Mm, I'm thinking how to code this. Okay, so my array A, okay, will be like a one if it's in that row and column. So okay, let's try to do it for one array first. One if I equals to row, or j equals to row equals to column. Linear algebra may be able to solve it actually, because like if you use Gaussian elimination, okay, it could actually solve the problem. Yeah, I don't know. Let's just try to solve using linear algebra first. I mean, we don't give up hope for this. Okay, let me just try to hard code this. Okay, so if let's say I have this number here, I want to add in 1, 3, 5. Basically, I just want to add in like 0, 1, 2, and then here. So maybe what I just need to do is not, it's not like that. What I want to do is I have an list of numbers I want to put in. So maybe like, okay, so maybe like um, indices, okay, equals to for I in range cell, in range size, for j in range size. Okay, so each of them indices will be, what will be my indices? my indices will be, if let's say I and j, this value here, it will be I times equals to, I'll add in, like for this one, I'll add in all my indices on the rows and all my indices on the column. So it could be something like, it's actually it's a it's a it's a four times loop, right? Yeah. So in order to get my indices, okay, so what we can do is, um, okay, maybe my first loop don't need to be like that. My first loop can just be size times size. Okay, so what we do is we can do my my in my indices can be like this. So over here, after we add in the indices, okay, over here my indices dot append indices. So over here my indices will be 0, and then I'll add in my indices. This problem is deceptively simple actually. Yeah, it's deceptively simple. I thought I could solve it, but I can solve only until 5 by 5. But at the 11 by 11 I got stumped. Then I can't solve it anymore. So now the solution that I'm trying to go for is a linear algebra, and I see whether linear algebra can solve this problem. So who knows, maybe the Gaussian elimination method can solve it. Yeah. So yeah, let's try it out. K in ray size, I'll kill my indices. If, okay, so this will be my row and column, okay. Then I will also need to loop through one more time for, yeah, so it'll be four loops actually. It's, yeah, 30 to the power 5. No wonder just now, I think someone mentioned 30 to the power 5. I think it was either coffee or OB. Yeah, I think 30 to the power 5 will work, will run. Yeah. So this is 30 to the power 5 in loops if we do linear algebra. So let's say if we do this for L in range size, okay. So this is one way to do it. The other way I can think of doing this is like, because like this is almost an approximate solution already. We have like reduced the problem to a simpler one using like a heuristic, and then we can just do simple swaps of the rows and columns, and hopefully this will lead to the answer. This can be done using optimization approach, maybe GAs or something, genetic algorithms. This could be done like that. But now what we try to do is, okay, maybe I should put this in the comments. Pursue a linear algebra solution? Question mark. I don't even know whether this works. Okay, let's see whether this works. So for J in range size, for K in range size, L in range size. Okay, so L, maybe this L is like index in range this. Actually, I think this front loop already did that job. Yeah, let's put it like that. For I in range size, for J in range size, and then for index. Okay, so my indices will append this in the. Okay, if, okay, index percent J percent size is 0, is I, okay, I mean, let's say we talk about this, I is the row, right, and this is the column, so this is J. Okay, if this is true, okay, or index divided by size is I, okay, then the indices we dot append index. So this will be my index for that particular, so then my indices will append this whole thing. So if you look at the linear algebra here, then we have this whole thing is already there. So this will be np dot array my indices. and then we have this. Let's just print out x. Okay, try the 3 by 3 problem. Okay, last two dimensions must be square. Okay, what does it mean? Okay, over here this 1 2, right? Okay, let's just print a here to see what my a is. 0 1 2 3 4 5 6. Whoa, 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 whoa. Okay, this a bit too many numbers in the index. Oh, okay. Yeah, silly me. This should be outside. Oh wait, no, no, no. What am I doing? It should be here. And then this one should be here. Yeah. So many things wrong in that loop. Yeah, okay, now this does look like it. Okay, so I print A. Okay, it somehow seems that I'm having too many indices. So like if I do here, okay, so this one should be here. Oh, this looks good. So these are all the numbers that I need to add up to like this certain number here. Okay, so all right, let's print x and see whether it solves. Oh, last two, 1 minus 1 maybe. Print a dot shape 95. Okay, print b dot shape 19. Okay, so it should be the other way around. It should be minus 1 1. Okay, this is shape 2 2, and this is of shape 1 2. Mm, I must have a square matrix, is it? Oh, okay, because these are the indices. Okay, so actually what I should do is like I should append 1. So this one should be minus 1. Okay, so I have a linear algebra solution like that. 1 1 1. Oh, actually it's not bad actually. Yeah, like if we round this off. Oh, oh, uh, can we do an int? Yeah, 9 unknowns, 9 equations. That's what I'm trying to do here. Yeah, Murat, I tried to use like a heuristic to take out the things one by one. But once I use the heuristics, I realized my heuristic is just basically take the row and the column sum of the numbers and then just see which is the highest and then I take it out from there. But I realized if I do that, it failed to do some cases. Yeah, so the heuristic method didn't work fully. It gave quite a close solution actually. So if just doing some tweaks at the end of it might be able to solve the problem. But I'm just seeing whether linear algebra can work. Yeah, I solved until 5 by 5 already. It's just that 11 by 11 is not possible right now. So yeah, let's just see whether this heuristic thing works. I mean, it looks like it's working. See, it gives some answers. So it's actually not bad. Actually, if you ask me, yeah, we can actually just use this. Yeah. So what we can do is instead of using fortress, we can just use like new x equals to 1 times this. Or actually, we can just use like that. Yeah, new x. Okay, I times size plus j. Dot and o. Oh, I deleted away the print, is it? Yeah. So to print the s here. Yeah. So this is the linear algebra method. Oops, saved it accidentally. Oh, what's wrong here? What happened? What happened to my linear algebra? It's not printing out this for some reason. It's supposed to print out this as well. Yeah, this actually should be a 1, right? If you look at here, it's not printing out. So maybe what I can do is x minus 1, okay, absolute x minus 1 greater smaller than epsilon. So maybe we just put epsilon equals to 1 e minus 9, something like that. Okay, yeah, we have more right now. Yeah. So like this. Don't print this anymore. Oh, it works for 5 by 5. Yes! Linear algebra rocks. Okay, everyone, we should all learn linear algebra. Yeah. Oh my gosh. That means what? Heuristics don't work for this problem? Yeah, what? I'm so disappointed. I thought heuristics would work. Oh no, heuristics doesn't work. Failed heuristics approach. Okay, work to 5 by 5. Okay, so this was the iterative remove element approach. And then there's a fortress here. So all this can be like, oops, let me just comment my code for people who want to see it next time. Yeah, so yeah, this was the failed code. Okay, these num pieces actually don't really need this. Okay, the check constraints actually also don't need because we didn't really use it in the end. Iter tools don't need. Yeah, so essentially this was the code. The failed heuristics approach is here. Yeah, so so what? We need to use linear algebra to solve this. I guess linear algebra works because it is a Gaussian elimination kind of method. Yeah. All right, let's submit this and see whether it works. Yeah. Murad, do you use the same kind of thing that I did? Yeah, I was also thinking whether genetic algo can solve the problem. So I might code this out using the genetic algo way soon. Basically, if we use the layer cake approach, okay, if we use the layer cake approach, we might be able, okay, I keep saying layer cake, but y'all might get the wrong impression. The layer cake is just a heuristic. where I take the sum of the row and the column, I add up all these numbers, and then I just see whether or not that number is large. So if that number is the largest, then I assume that is an O position. So that approach has got me far. Okay, it has solved until 5 by 5, but it didn't work for the higher numbers. So for the higher numbers, apparently you can't use that. You have to use constraint maximization problem like linear algebra. Actually, I didn't solve the problem at all. I just used I just used linear algebra. I mean, this solver actually is actually more complicated than what other people than what is needed for this problem, because in this problem actually it's like a simplex search where you already have a binary like a 0 1 point. Yeah, I have a feeling that this field heuristics approach can work eventually. Okay, if if I use some form of genetic algorithms to like swap the row and column that has mismatch. Yeah, so that because genetic algos, if you use it to solve the full-blown problem right at the beginning, I think it will fail, because how do you define the chromosomes? Okay, you have to define it as either 0 or 1 for the O's, right? But there's so many O's. I mean, 31 times 31, which is like 900 over chromosomes. You want to do the swapping. Let's say you swap is 900, choose two possibilities of swapping. That would be forever for you to converge for GA solution. And it's not that if you swap, it will definitely be better. It might actually be worse off first before it can be better. So how many populations of people do you want to keep for GA to solve this? So I don't think you can keep a GA to solve this. Yeah, but I'm not too pleased with my solution either, because I'm just cheating. You see, everyone, this is a cheat solution. Okay, we just basically use a linear algebra and solve it, and voila, it's solved. Okay, let me just submit this and see whether like other people have a better algorithm. Okay, all right, logic. Okay, everyone, if you are interested to get 50 experience points, linear algebra. Okay, linear algebra solves this problem perfectly. Okay, let me just rate this. Loved it. Okay, let's see the solutions for this puzzle. Everyone uses linear algebra. Yeah. Okay, so this is exactly the same as my solution. This solution 2. Row plus size, MP dot ones. Everyone uses linear algebra. See, yeah, it's exactly the same. Yeah, it's no brainer. Yeah, I mean, if you ask me which one I prefer solution two's first part, but I prefer solutions one linear algebra here. You know what? I prefer my own solution. I prefer my own solution. Yeah, none. I prefer none. Yeah, I mean, it's like so. I prefer one actually. Yeah, one. Budding examiner. What is this? Next review. Two reviews left to access the best solutions. Can you not subject me to this thing? Yeah. Everyone uses linear algebra. Look. Okay, this looks like a shortest mode problem that people are trying to solve. Wow, read dot find all. Wow. instead of in, instead of doing like epsilon, he just found whether the number contains 0 point in order to see whether it's zero. I mean, that's a bit excessive, isn't it? I mean, it's like using a search to solve a a simple solution. Like this will definitely increase runtime. I mean, so yeah, first solution is out. Let's see this. We can see that the grid is through a linear system of equations. Yeah, this is a linear algebra thing again. Okay, solution 2 is better. Yeah, solution 1, what is this? Why will you use a search thing to just do what you can do with numbers? Yeah, what's this? Yeah, that's bullshit. Okay, that's bullshit. Next, I'm so sorry. I mean, whoever wrote that code, I didn't mean to insult you. Okay, I just think that it's unnecessary to use a regex solution in order to check whether number is 0 or 1. Yeah, code golf. All right, let's see this. Over here we have size. Everyone's using linear algebra. Yeah, I'm actually quite interested to see whether you can solve this with a layer cake heuristic. Yeah, I don't know which one do you prefer, one or two. I mean, I'm neutral to both of this. I mean, honestly, it's about the same to me. Yeah, yeah, I quite like this NP dot vectorize. I have no idea what this does, but it looks cool to me. Yeah, anything with the at the top looks cool. Yeah, it's like can't remember what's this called in Python, but it like wraps your function with something. Yeah, in this case, I guess it vectorizes the NumPy array. Yeah, I don't know. I like this solution better. Yeah, because it has this np dot vectorize. Yeah. All right. No, it's showing Python because I coded in Python. All right. Okay. Let's see the other solutions. Kayo is a good coder. Let's see his solution. Also a linear algebra solution. Okay, upvote. Yeah. Okay. Benefits of being my friend. Yeah. Upvote. All right. Murad, where's yours? Murad, where's your solution? Wait, where's the answer? Yeah. Oh no. Browse the best solutions. All right, Murad. Well, it's this definitely deserves an upvote. Yeah. Look at this. So concise. Yeah. Look at this. Yeah. Just checking the. Yeah, this is so much better than using regex. Yeah, whoever used regex for this. Okay, let's see the forum. No, I think all languages have some form of yeah. Oh, if you clash against Murad, you are clashing against a pro. I tell you, Murad is a pro. Okay, so far I've learned more from Murad than he has learned from me. Yeah, let's put it that way. Yeah. Okay. Sorry. Let's see who's one. Husoki. Let's see. Husoki. No, it didn't seem to work. Like utterly defeated me for a few days. Yeah, it defeated me for a few hours. Oh man. Gaussian Jordan algorithm. This guy just gave the answer. I use Python as specifically numpy.linearalgebra.solve. I'm proud of solving it in 10 lines of code. 9 lines of code with no library. Is it? ON squared. Murat, where's where's Musako's oh, okay, you gave me the link. Okay. Let me copy and paste this link. I'm still very disappointed my layer cake didn't work. Yeah, it looked sounded like such a good solution. So key upvoted. Yeah. Okay. Let's see. Okay, this is just to find the number. Okay. Yeah, this is to sum. Okay, yeah. All right. And then we sum all the row sums. Grid num divided by this is the number of pieces. Okay. Yep. And solution row sums equals to s minus solution number. Oh, there's a heuristic for this. S minus solution number divided by size minus 1 for S in grid row sums. Mm, why size minus 1 though? I mean, I understand this. I got this myself too. This is to find the number of pieces by taking the total number of sum of the row and columns, and then I divide by 2 times sum minus 1. Yeah. But why is this the solution row sum? So I guess this means like the number of pieces in each row. So this is taken by given by S minus solve sum, S minus number of pieces. What's S? S in grid row sum. So in each one, I minus the number of pieces. I divided by size minus 1. That will give me the row sum, and then this column sum. And then to get the solution is row sum plus column sum minus grid ij minus the original one. This on squared to solve this. Yeah. I don't understand this solution, I must say. Yeah, I mean, I quite like the idea that you get the row sum and the column sum. Okay, but how did they get this? I mean, granted, this solution sum is the number of pieces that we have, and then we just take the number of total sum in each row minus the number of pieces. He calculated in row sum, column sum, the current cell is repeated twice. You mean for this part here? Yeah, I did use something like that also. So you take the rows and you take the columns and then you minus off the current position. So I guess this solution row sum is just like the total number of pieces in each row. And this one is total number of pieces in each column. And then this one will be um the grid count itself. So if let's say your row and your column counts like add up to a certain number, and then your grid minus off this one, if you have a piece on that grid, okay, then this two minus off this one, okay, will give you 1. But if you don't have a piece on that grid, then this two minus off this will give you 0. So I get this part. I get that part. So by doing that, you can get the current number. But how is this part giving you the row sum? How is this part giving? How is this part? How does this tell you the number of pieces in each row? So that's the biggest question that I have here right now. So like I know solution sum, it is the number of pieces, the number of O's there are in the entire grid. But why S minus solve sum? Why S minus solve sum? Okay, so you take the difference between your row sum and the yeah, I have to go and try out this solution. Yeah, let me just copy and paste this. Yeah, so this actually gives me the number of row and column in each. Yeah, so let me try to see, okay, what is S? Oh no, grid row sums. Okay, so solve sum is 3. That's the number of pieces. We derive how to get this. So S minus solve sum, okay, divided by size minus 1. So let's talk about grid row sums. So it's 573. So let's minus solve sum, okay? So if I do a minus source sum like that, um, okay, if we minus 3, that will be like 2. This one will be 4, and this will be 0. And then we divide by this, which is 2. Okay, let's print this without the dividing by size minus 1. I just want to see whether this really... Oh, it's actually all divisible. It's not it's not approximation. This is actually divisible. So if let's say my row sum is s, okay, let's just take a look at this. If I take my row sum, okay, which is here, my row sum will actually already take into account the entire amount of pieces that there are. So this row sum here, if I minus away the number of pieces, okay, because each piece over here will affect the row, okay, s minus 1 times, I think it has to do with something with repeating pieces. So let's say I talking about this row here. This row has 1. So if I minus away the solution sum, okay, I minus away the number of pieces. So I minus away this one. The contribution to this is 111. So if I minus away this one, the the contribution to the row sum, okay, will be... So these two pieces will contribute 1 to the row sum because of this and this piece. But any piece over here, any piece in this row, okay, will contribute to the row sum of 3, 111 of 3. So because I subtract away the sole sum, whatever O's that are on this row itself, okay, will be subtracted away, okay, which leaves each piece on this row will affect size minus 1 because I subtract away this piece here. So if I take away this s minus sole sum, so anything that is not in this row, right, will only contribute a sum of 1 because of this contribution term here up. So this piece over here, okay, so any piece that is not in the row will only contribute a sum of 1, okay, to the row sum. And by subtracting away the solution num, I take away all this contribution of the non-row pieces. So I'm only left with only the row. And then when I subtract away the row, each piece of the row will only affect size minus 1 times because of the remainder. So by taking away this and then I divide by size minus 1, I can effectively tell you how many pieces there are in each row. I repeat the same logic for the column. I can get this call sums. And then what I can do is I can take the row plus the column minus the actual number itself, okay, to tell you whether or not a piece is there. Because if a piece is there, the row and column will double count itself. And so it'll be a 1. So actually this solution is, I understand it fully now, is ingenious because it takes into account that the O that is not in the row that you're looking at will only affect the row sum once. For every O that is not in that row, it will only affect the row sum once. So any O that is in that row itself will affect the row sum, okay, after you subtract by 1. Okay, before you subtract by 1, every O in that row itself will affect the row size number of times. So that's why, because when we minus away the total number of pieces, we divide by size minus 1, that will give you the row sum itself. So just now, I think Coffee Cafe or Omniscient, one of you all were asking like, what is the row and what is the column, right? And indeed, if you know what's the number of pieces in each row and the number of pieces in each column, you can actually solve this problem very easily. Yeah. Yes, yes. So actually, Omniscient, but you have the makings of a good programmer. You figured out how to solve this in the right solution, in the right thinking. Yeah, you found out how to solve this in the right thinking. The only issue is that I didn't know how to come up with the row and the column sum. I mean, now that I look at his answer, I reverse think. I think it's ingenious. I actually understand this now. I think it's great. Murad, if you are still here, I'm not sure if you are still here, but I figured it out. I figured his solution out. This is the P equals MP thing. If you look at a good solution, you can figure it out. That's MP. But if you can figure out how to solve it, it's P. But anyway, that was a fun problem. I think this was a fun problem. It taught me quite a bit. Yeah, also taught me that linear algebra is very useful. Yeah, this is like n to the power 4. I still have no idea how this linear algebra actually works, actually. Yeah, but yeah, I mean, it works. It works. My linear algebra method worked. Uh, I'm happy for it. Yeah. I'm thinking actually of trying GAs on this problem actually. I think GAs can work. Okay, y'all might think that is stupid, but there's some merit to this problem because this problem is like finding the optimal solution in a hyperspace in a complex dimension of space. Yeah, so I think if with enough search, I just wonder whether it will meet the time limit. With enough search, GAs might solve this problem. Yeah, I mean, I leave you on that note. Yeah, but of course, if we can find the exact algorithm, it's like GAs can decide which O's to swap. Yeah, so it is in the case that like you have a very very approximate solution already. Like for example, I use my layer cake approach. I already get a very approximate solution. Then at the final bits, GAs can do some swapping. Yeah, I mean in the beginning, if we were to use GAs, it's probably okay for small grids, but for large grids, if we use GA right at the beginning, it will be very messy and chaotic. Yeah, but if like we use some form of heuristics already, then we apply GA on it, I think it can work. Okay. But I mean, I'm just saying like this. I don't think I have the time to try it out. But uh, tomorrow I'm busy, so I can't stream tomorrow. But I'm definitely interested to try to see whether GA can solve this problem. Yeah, because I think GA's. I mean, if you look at my blog, the delving into tech.blogspot.com, I recently posted a post on GAs. I really like the idea that you can just like train a population that gets like fitter and fitter that tries to optimize the solution, and then eventually after enough generations you should be able to stumble on something very close to the solution. Yeah, no, GN Monte Carlo is different. Okay, Monte Carlo is like randomly guessing the solution, so we can also do Monte Carlo for this. Is 2 to the power of 31 times 31 number of guesses, and then you like try to it's basically brute force, but brute force in a random guessing way. That's Monte Carlo if you use it in this problem. GA here is different. GA, the chromosomes are, in this case, the chromosomes will be the O's itself, and then we try to swap. Yeah, so have to think about it, how to express it in a form that is easily like um, that doesn't explode exponentially when you solve it using GAs. Yeah, possible. Swap strength by probability. Yeah, you could do that. I still think Monte Carlo for this is a little too hard. Yeah, I myself am a big fan of Monte Carlo, but I don't see how Monte Carlo can scale up that well. Monte Carlo is great if you can what do you call it? Okay, you are making an assumption here. You are making that an assumption that GA is Monte Carlo. Yeah, that's not exactly true. That's not exactly true. Yeah, yeah, sure. Let me try to solve this problem with GAs. Okay, but I may not make it in time for the end date of this problem because the problem ends in 1 day 5 hours. Tomorrow I can't code because tomorrow I'm going out. Yeah, but I think I will try to solve this problem after it's done. Yeah, I think can solve problems that have been solved. Yeah. No. GA is basically just trying to optimize the swaps randomly. So actually there's an element of randomness in GAs. Okay, because you do let me just show you this. Yeah, let me just go to this one. Yeah, so I recently put a blog post on this. So I think if you were to use GAs, okay, like over here, the fitness assignment would then be the amount of like the fitness assignment will be how close you are, okay, to the calculated values for the like over here. If you use GA for this problem, it will be how close you are to this grid. What's the difference? That will be GA. Will I solve the traveling salesman optimization? Oh, you mean there's something else in coding? Yeah, I'll take a look at that. Okay, I haven't taken a look at that. Yeah, but I'm just quite curious to see whether, because now we have solved this problem with linear algebra. I want to see whether my heuristic method, which failed, which was very sad. I almost thought it would work. Yeah, if it worked until 5 by 5. If I supplement it with, okay, maybe over here to do GA solution after layer cake. Yeah, so maybe a GA solution might work. Yeah, but the linear algebra method definitely worked. Okay, this got me the, okay, this one is soft. Okay, using linear algebra works for this problem. This is the n squared solution that was given by Hisako. It works also using calculating what's the row and the column. Okay, and then you can get the solution. Okay, this was this is Hisako's solution. Okay, so this worked. Okay, now what we want to do is we want to see whether we can do a GA. So how can we do this GA on this problem? Is it possible to use GA to solve this problem? I don't know. Yeah. Okay, but basically what I want to do is for this chromosomes. Okay, the chromosomes will be really just this. There is a 1 if it's a O and a 0 if it's not. Okay, then we just see whether we want to like do some swapping. Yeah, so we need to find out a way to do some operations to, so like this crossover needs to change. Okay, it may not be just like a crossover from parent to, it could be a swap. Yeah, so maybe it may not be GA after all. It may be doing some operations like simulated annealing. You swap the position, see whether it works. But we will keep a population of that so that we can do these random swaps on that population itself, and eventually one of them might swap until it hits the solution. Let me think about it over sleep, and then like just check out my Twitch channel if I decide to solve it with GA. I think it's possible. I'm quite keen to try it. I mean, you know, why not, right? I mean, I'm almost there. If you use the layer cake method, actually, is very, very, very close. Let me just show you all again. Okay, for those who haven't seen this layer cake. Okay, okay, let's take this away, and then this was the, so in the layer cake solution. Okay, oh, MP is not defined. Oops. In the layer cake solution, like this 3 by 3, all this is soft. Okay, all this was soft. Okay, 5 by 5 is soft also. 11 by 11, okay, you see it has this -1 over here. So if we can figure out a way to like swap the position such that make this make this sum of the cell count, make it 0. Yeah, we may be able to solve this after using the layer cake heuristic. We may be able to solve it using GA. Yeah, and you're right, Coffee Cafe, that the GA might be stuck in a local minima. Okay, but actually GA is least likely to get stuck than like gradient descent algorithms or neural networks, because GA, when you change the chromosomes, you might jump from one area to another area in the loss landscape or the optimization landscape. So GA actually can work well for problems where the solution space is not continuous. It can be very discrete. You can have a solution here, you have a gap here, and another solution here. GAs can actually jump here and there if you use the right approach. So there's GAs, there's a particle swarm optimization, which also works for this kind of problems. Yeah, I'll try to use GA for this. Okay, anyway, it's late now for me. I've got to go. I hope it's been interesting watching me solve it. I myself have I myself enjoyed solving this. I'm just not very satisfied that I solve it with the linear algebra method, because I feel that's a bit cheating. I mean, it's essentially telling You okay? This is quite obviously a linear algebra method, right? Yeah. So yeah, not too happy that I solved it with linear algebra. I mean, you can also solve Sudoku with linear algebra. Yeah, that's true. That's true. Solution is solution. Yeah, but yeah, I do want to see whether we can solve this problem with GAs. Yeah, that'll be interesting to see. Okay. Yep. Anyway, I've got to go, and yep. See you around. Okay. Bye bye.